let's suppose we have a charged particle Q that is moving with a velocity v to the right, and it's going to enter a region where there's a uniform magnetic field. We know that because this particle is charged and because it has a velocity, it's moving, then when it enters the region where the magnetic field is, it will feel a force, a magnetic force on that charged particle. The direction of that force depends on the charge and the orientation, but the force will always be perpendicular to the velocity and perpendicular to the magnetic field. And so suppose now that this positive charge enters the region where the magnetic field is, what direction would it feel a force? In order to determine that, we've used the right-hand rule. We take our right hand, we point our fingers in the direction of the velocity, which is to the right, and we have to turn our hand such that our fingers are able to curl in the direction of the magnetic field, which is kind of, out of the screen toward you. And so you have to turn your hand a little bit, and when you do that, your thumb will be pointing toward the bottom of the screen. And so this charged particle, this positive charge, would feel a magnetic force which points toward the bottom of the screen. And then, of course, if this were a negative charge, then it would feel a force in the opposite direction. It would feel a force toward the top of the screen. And so when this positive charge enters this region, it has a velocity and a force which are 90 degrees apart from one another. They're perpendicular relative to one another. And so the type of motion that we get when the charged particle enters the magnetic field is circular motion. And the reason for that is not only because the force and the velocity are perpendicular, but if we were to imagine what the subsequent path of this charged particle would be, is it would be moving forward, and the moment it gets into the magnetic field, it would be deflected downward, and the path that it would follow would be an arc that would describe part of a circle, right? Because as the charged particle makes its way in, let's say at some moment later it's here, the velocity, its direction has now changed. It's pointing down and to the right. And the force would also change. The force would now be pointing in this direction. And so you can imagine how the velocity and force vectors would follow the charge around and bend as the charge makes its circular path through the magnetic field. If the region of the uniform magnetic field were large enough, then the path that this positive charge would take would just be a circle. At all points in that circle, the charge would have a tangential velocity v, and it would have a force, that magnetic force, which points towards the center of the circle. And so no matter where it is, the charge would be in uniform circular motion. Since we've studied circular motion before, we should be able to relate the force to the acceleration experienced by the object, right? We know that if the direction of the velocity is changing, although the velocity is constant, the direction of the velocity changes, which means that there's a change in velocity, and if there's a change in velocity, then there's an acceleration, and that acceleration is due to this magnetic force. So we know that in circular motion cases like this, then the acceleration is a centripetal acceleration, which is given by v squared divided by r, where r is the radius of this circle that I've drawn down here, and v is that tangential velocity. We also know that force, mass, and acceleration are related to one another through Newton's second law. And so the force that acts on this charged particle is the magnetic force, Fb. The mass of the particle, let's say, is m. And the acceleration of the particle is the centripetal acceleration, which is v squared over r. And so if we know that the magnitude of the magnetic field, Fb, is given by q v b times the sine of the angle between V and B, then we should be able to combine these two equations and better understand the circular motion of the charged particle. If the velocity and the magnetic field are always perpendicular, they're 90 degrees apart, and so if the velocity and the magnetic field are perpendicular, then the magnetic force is given by just QVB, because the sine of 90 degrees is equal to 1. And so now what I'll do is I'll equate that expression for the magnetic force, QVB, with the equation up above, which is mv squared over r. While this equation could be valuable for a variety of reasons, one thing that it points out is we can figure out what the radius of the circle will be of this charged particle in a magnetic field by rearranging this around. So I'm going to solve this for r. R is given by m times v divided by q times b. And so if I know the mass of the charged particle, the velocity of the charged particle, the charge, and the strength of the magnetic field, then I can tell you how big of a circle that the charged particle will be moving in when it enters that magnetic field. Another important quantity which describes the motion of this charged particle is the period, which we represent with a capital letter T. The period is the amount of time it takes for it to complete one full cycle, and that period is given by the distance that the charged particle needs to travel, which is 2 times pi times the radius of the circle, which is the circumference, right, of this circle, divided by the speed that it's traveling with, which is v. If you remember, back to when we studied rotation, we learned that things that are moving like this, they also have an angular speed. We could describe how fast it's moving with an angular speed. So that would be measured in radians per second instead of meters per second, like the linear velocity, and we represent that quantity using lowercase letter omega. The linear velocity and the angular velocity were related in the following way. We had v equals r times omega, so they're related through the radius of the circle. Making that substitution down below, we would get 2 times pi times r divided by r times omega, which was a relationship that we saw before. The period is given by 2 pi divided by omega because the r's cancel. And so if I know that v equals r times omega, I know that the period is 2 pi divided by omega, and I have the equation in green, which I've circled. The combination of the three of those things should allow me to describe the period of the charged particle in terms of the charge, the mass, the magnetic field. And so now I'll leave it to you to combine the v equals r omega equation, the period equals 2 pi divided by omega equation, and the equation that I had for radius up above to show that the period of the motion of this charged particle as it moves around in a circle is given by the following equation. The period is equal to 2 pi m divided by q times b. And so here I have two equations which it took me a little bit of work to get to, but derived equations for the radius of that circle and the period. And you should take a moment to make sure you know which things affect the radius and which things affect the period. For example, one very important relationship is that as the speed v increases of the charged particle, the radius of the orbit that it will travel along increases, but the period stays constant, right? The linear velocity v shows up in the equation for the radius of the circle, but it doesn't show up in the equation for the period. So that's at least one important relationship that you'll be expected to know. One of the exciting things about learning how charged particles move in a magnetic field is you can learn how a mass spectrometer works. You might have used a mass spectrometer before, but even if you haven't, it's a pretty interesting device, and it's one that's really important for understanding the types of things that we're studying right now. So in principle, a mass spectrometer is a device that allows us to measure the masses of different isotopes. And the way that it does that is you take an atom and you remove an electron from that atom, which ionizes the atoms. And so now the ions are positively charged. If we remove an electron, then those ions that are left over will have a positive charge. If we then apply a potential difference, delta V, between the ion source and the region where the magnetic field is, then as the ions travel from the ion source to the magnetic field, there will be a loss in potential energy, right? There will be a decrease in potential, and so those positive charges are losing potential energy. And the way that I can express that loss of potential energy is through the equation delta U equals Q, the charge, times delta V, the potential difference that I've drawn in red. As the charge loses potential energy, it gains kinetic energy, it speeds up. And the gain in kinetic energy will be given by delta K, which is equal to 1/2 mv squared, where the initial velocity of the charged particle was 0, and by the time it reaches the region where the magnetic field is, while it's lost potential energy, it gains kinetic energy and will have some speed v. So essentially, if you're able to keep up with that, we make some ions, we are going to accelerate them across this potential difference, they lose potential energy and they speed up as they move from the ion source up to the place where the magnetic field is. And so by conservation of energy then, the increase in kinetic energy, 1/2 mv squared, should be equal to the decrease in potential energy, which is Q times delta V. If I take that equation and I rearrange it for the velocity of the charged particle, what I get is that V squared is equal to 2Q delta V divided by the mass of the charge. And now what I want to do is I want to focus on what the charge is doing. Here at this open region, there's going to be a grid there, and that charged particle will pass through the grid. So I'll draw the path of the charged particle in green. It'll travel in a straight line until it hits the place where we have this uniform magnetic field. The moment it gets there, if we point our fingers in the direction of the velocity and we curl them outward toward us in the direction of the magnetic field, it'll feel a force to the right when it enters that magnetic field. And that will cause a deflection, which makes it look like a circular arc, which is going to curve down and to the right. And so the path I'm going to draw in green might look something like this. It's going to go up in a circular arc and then curve back down and then hit this photographic plate, which I've drawn on the right. And so everywhere you could imagine what that velocity looks like when the charged particle is at this location. For example, its velocity would be to the right, and the force being exerted on it due to the magnetic field would be downward. What happens from here is the photographic plate will record the position that charge strikes the plate, and when it strikes the plate, we can record where along that photographic plate that the charge hit. And if we know where the charge hit, then we should be able to figure out what the radius of that circular arc that it went through was. And so in principle, if the photographic plate is able to tell us where the charged particle lands very precisely, then we can very precisely know what the radius of the arc was. And if we know that the radius is related to the mass of the particle, and so we should be able to determine the mass of the particle as long as we were able to determine other things like the charge and the magnetic field and some of the other quantities that show up in that equation. And so what I want to show is that that exact equation that we might use in this kind of a scenario. Previously, we showed that the radius of the circle is given by m times v divided by q times b. And up above, I had an expression for the velocity of the particle in this kind of a situation. So what I want to do is I want to combine those two equations. And I feel like the simplest way to algebraically do that is to just square everything. So I'll have, r squared equals m squared v squared divided by q squared b squared, which means that I can take my equation from up above and substitute it in because it was already solved for v squared. So when I do that, what I get is 2q m squared delta v divided by q squared b squared times m. And when that simplifies, what I get is one of the q's will cancel and one of the m's will cancel, so I'll get 2m delta v divided by qb squared. And remember, this whole thing is equal to r squared. So now if I take this and I rearrange it for m, which is ultimately the thing that this device is supposed to be able to tell us, the mass of this charged particle is given by q times b squared divided by 2 delta v times r squared. Right? R squared was what that quantity down below in white was equal to. And so this is my expression for the mass of the particle in terms of other quantities which we should be able to know, right? The potential difference, delta V, is something that I can control. The radius of the circle that the charge moves in is going to be figured out by where the charge strikes on the photographic plate. The charge is something that I should be able to figure out based off of what types of ions I'm making in the ion source. And the strength of the magnetic field is something that I can calibrate and measure independently. And so I can figure out the masses of individual charged particles, which is something quite complex, using this kind of a method, using a mass spectrometer. One thing I'd like to point out is, all the circled equations, which I'm kind of labeling as important in this video, they're not equations that are given to you, but they are equations which have reasonable paths to get to them. And so you should really make sure that you're able to follow all the things that I'm saying in this video, so that way if you needed to develop any one of these equations on your own, you would be able to put together the pieces in order to get there.